now we have to take the modulo. And here's a funny thing. In Java, you can use the bitwise AND operator with the power of 2 minus 1 as a replacement for modulo.
Good morning, everybody. Here are the guys from Germany. My name is Thomas, and my guest today is Achim. Good morning, Achim.
Good morning, Thomas. Hello, world.
So, Achim, day 15 of Advent of Code. Please explain us the puzzle for today.
Yes, we arrive inside the volcano, find a slightly panicked reindeer there, and are presented with the challenge to implement a hash function. The holiday ASCII string helper algorithm. This function is relatively simple. So we take a string character by character. We determine the ASCII code for the current character of the string. Increase the current value of our current value which is initialized at 0 by the ASCII code of that character. Then we multiply the current value with 17 and take the modulo by 256.
Okay.
So the implementation for the hash value looks from my side as follows. Okay, we initialize at 0. Okay, we take the character and already have the ASCII value.
Yes.
Add it into current value. Multiply current value with 17, and now we have to take the modulo. And here's a funny thing. In Java, you can use the bitwise AND operator with the power of 2 minus 1 as a replacement for modulo.
Is this faster?
It is faster.
Cool.
It is probably a lot faster because with modulo you have to really you have a job for your arithmetic logical unit, and this is a thing that is probably very much faster because what modulo 256 essentially does, albeit a bit more complicated, is kicking out every bit above these that comprise the number 255. And that way you have it faster by bit masking.
Okay,
so that is the hash algorithm, and for our puzzle input, we need to do that on every substring. We have a comma-separated list of operations and return the sum.
Yeah, looks straightforward and easy.
That looks straightforward. For the second part,
yeah, what is the twist for the second part?
We have a lot of text. So we have a set of boxes and we have a ray of light that has to go through it. And these boxes contain lenses that shall focus the beam of light. That is the rough idea. So we start with, we have 256 boxes, which can contain lenses with distinct focal lenses ranging from 1 through 9. And we have to put them in there and out and back out again. So we have two operations in our puzzle input. We have the dash or the minus. So if we encounter that, like here in the example, so we have a label and the minus, then we have to kick out a lens with the flag of CM that is stored in the box that we can find by putting that label CM through the hash algorithm.
Okay.
And then we search for such a lens and kick it out. The other operation is this equal sign. which is a replace or a set. So if we have a lens with that label in the addressed box, which we address the same as with the minus operation, then we replace it. If we haven't, we put one in. And if we put one in, it goes into the last position. And if we kick one out, the following lenses move one up. So it's more or less the functionality of the standard implementation of a list in Java that we can use for that.
Okay.
So my code for that looks a little bit awkward. So I have a list of these 256 boxes addressed from 0 to 255. And each box is a list of map entries. The idea was, hey, map entry has what I need, a key and a value, with the key being the label of the lens and the value being the focal length.
Yeah.
However, I found out a little bit later that I have to implement the entry by myself, and at that point I could also have thrown out the map entry interface.
What was the motivation to implement it by yourself? What did you miss?
I didn't have a proper implementation at hand. Normally, you access a map entry if you're working on with a map implementation. For example, hash map, hash table, tree map, something like that.
Yeah.
But none of that would really work here because we have an order by insertion, and the maps don't provide for that. So I could have built an entry class just with a key and a value, and that's it, and get rid of that altogether. So I did it this way. I didn't need it to, as I found out. However, we go through all the operations. If the operation ends with a minus, I take the lens identifier by substringing, throwing away the minus at the end, hashing it, going into the box, searching through that list for a lens that has the same name, and removing it.
Yeah.
Important here, use a while loop, not the for, because the for might break. And for the assign operation, I take the index of the equal sign. I could also have used the string split operation for this. And the first part is a lens name, and the second part is the, where is it? Where's my focal length? Here's my focal length. That is a focal length, and the lens name is also used for addressing the proper box. And within the box, I then look for a lens with the same name. And if I find one, I end here with the index j smaller than the box size. If it isn't, I add a new entry.
Yeah.
And for the end, we need to calculate the power of each length and sum it all up. So I go through all the boxes, take the index +1, So the box at index 0 becomes box number 1. And go all through the lenses. Their indices also added by 1. Multiply these with each other and with the focal length of the lens.
Yeah. And then you got the sum.
Sum
and
it
you
all up. Precautionary as along. Probably didn't need it, but who knows? I get a result.
Okay. What was the hardest challenge for you this time?
I messed up the substring operation and had a -2. So I found it by analyzing the puzzle and the test data that my delete operation didn't work because the lens ID I used here was 1 character too short and didn't kill anything.
But you found it. Nice. Some last words for the puzzle? Did you like it?
See. I did like it. It was a bit, it was a lot of text, yes, but I somehow did like it. And let's see what's in for tomorrow.
Yeah. Then we see us tomorrow, Achim. Ne? Thank you. Big thank you. And
Tomorrow.
bye-bye.
Bye.